In this video, we're going to go through a couple of problems on the homework sheet that is practice with neutralization reactions, strong acid, strong base problems. And I'm going to look at number 5, and then we're going to look at number 6 and number 7. So let's just read the three of them very quickly to see what's asked in this problem. So number 5, what volume of sodium hydroxide would you need to add to the 50 milliliters of 0.040 molar nitric acid if you wanted to completely neutralize the acid? And this sodium hydroxide is the 0.025 sodium hydroxide that's in the problems. Okay, so the first question, number 5, this is a neutralization question. And then number 6 says, what would be the concentration of all ions present in the resulting solution from the previous question? So this is also a neutralization question. If I neutralize the acid with the base, what ions are left in the solution? That's what number 6 is asking. And then number 7 is asking, calculate the concentration of all ions present in the solution when 5 milliliters of the sodium hydroxide 0.025 is added to 50 milliliters of the nitric acid. And so this question is not a neutralization. This question is saying, we don't know if it's a neutralization. It's saying, I'm going to mix two amounts and you're going to have to figure out which is limiting and what's left over. So let's start off with number 5. We did a couple samples of number 5. We did a couple problems that were similar to it in class. So we have nitric acid is going to react with sodium hydroxide. And I'm writing aqueous if they dissociate. Strong acids dissociate and sodiums dissociate. And we're going to make sodium nitrate, aqueous, and water. Now, for number 5, we're asked what volume of sodium hydroxide, so that's the question, and the molarity of the sodium hydroxide is 0.025 molarity, is needed to neutralize 50.0 milliliters of the nitric acid, that's a 0.040 molarity. Okay, so neutralization means you're going to run out of both the acid and the base at the same time. So neutralization is when stoichiometrically you figure out exactly how much base do I need to react with this much acid so they both run out at the same time. So let's calculate the stoichiometry amounts. And so we're going to look at, we need to get these numbers into moles. So how many moles of nitric acid do I have? And when we do 0.05 times 0.04, the molarity times the volume, we find that we have 0.0020 moles. Well, we can do the stoichiometry and say 0.0020 moles. I'm going to do it a little bit lower. Just move this up a little bit. Okay, if we did the stoichiometry, we'd say 0.0020 moles of HNO3, and I need 1 mole of NaOH for every 1 mole of HNO3. And so I'm going to need 0.0020 moles of sodium hydroxide. So I'm going to need the same amount because it's a 1-to-1. That makes sense, 0.0020 moles. And then I can find the volume because I know that when we're doing solutions, we know that N is equal to M times V. So the volume is going to equal N over M. And so the volume that I need is going to be 0.002 moles divided by the molarity, 0.025. And we find that we need 0.8 or 80 milliliters. That's what we need. Okay, so that's the answer to number 5 rather. For number 5, we need 80 milliliters. Now I left some space here because what we're looking for in number 6 has to do with this problem that we just finished. So for number 6, it says, what would be the concentration of all ions present in the solution from the previous reaction? And so number 6 is saying, okay, after you do that reaction, I'm going to have 130 milliliters of solution. I'm going to have 80 plus the 50 of the nitric acid, right? So now I have 130 milliliters. And what's in there? So I'm going to go back down to this reaction here, and I'm going to start with this row. I'm going to call this my initial row. And then we're going to watch what happens in our reaction using an ice table. Now remember, in an ice table, the change row in your ice table is telling you, I'm going to erase my molarity calculation here. The change row is telling you what happened, what stoichiometrically happened in this reaction. And so what we calculated with our stoichiometry calculation was I needed a 1-to-1 ratio. So when I do this reaction, I'm going to use up 0.002 moles of nitric acid. That will be gone. And because it's 1-to-1, I'm also going to use up 0.0020 moles of the sodium hydroxide. It will be gone. But I'm also going to make, and since this is a 1-to-1, I'm going to make 0.002 moles of sodium nitrate, and I'm going to make 0.002 moles of water. Now, I started with none of these. I mean, there was water in the beaker, but in terms of this reaction, I'm forming sodium nitrate and water. And so in terms of the reaction, I'm saying there was no water when I started with the HNO3 and the NOH. And so I'm making 0.002 moles of sodium nitrate. And I'm making 0.00, I'll have at the end that many moles of water. Now, this is a small enough amount that it's not going to impact our milliliters. We're going to ignore it in our milliliter calculation. We could actually add it in, but we're not going to worry about the water that we make. What we're going to look at is we have this many moles of sodium nitrate that we've made. So sodium nitrate, at the end of the reaction, I'm going to end with 0.0020 moles of sodium nitrate, right? So this doesn't go with number 10 or 11. This is just number 6 I'm doing. Okay, so in my beaker, I'm going to have, that's going to separate out. I'm going to have 0.002 moles of both sodium ions and nitrate ions. And so when we calculate concentrations, remember the concentration is equal to the number of moles over the volume. And so the concentration of these two ions is going to be 0.002 divided by 0.130, our 130 milliliters. And so the concentration of my sodium is going to be 0.015. So in my beaker, I'm going to have sodium ions, concentration 0.015 molarity, and I'm going to have nitrate ions. The concentration is going to be the same because the number of moles in the volume is the same, 0.015 molarity. Okay, so now we're going to do number 7, and number 7 is not a neutralization. Number 7 is saying, let's compare number 7 to number 5. So our number 5, we found out that for 50 milliliters of 0.04 molar nitric acid, we needed 80 milliliters to neutralize it. For number 7, it says for 50 milliliters of 0.04 molar nitric acid, what if we only add 5 milliliters? Well, that's a lot less than the 80. So I'm definitely not neutralizing all my acid in this one. I'm not in this one. Instead of adding, like in my original problem in number 5, I added 80 milliliters. If I don't add 80 milliliters, then I'm not going to use up all my nitric acid. And so in this problem, it's different. It's more like the precipitate problems where we had spectator ions and we had some leftover excess ions. So we're going to set this up. We're going to write our reaction again. We had sodium nitrate. I'll put it in the same order. We have nitric acid reacts with sodium hydroxide, and it makes sodium nitrate and water. And the nitric acid is 50 milliliters of 0.040 molarity. And so we already know from the last problem that's 0.0020 moles. Now in this case, we're going to add 5 milliliters of 0.025 molarity. And when we do that, we find that that's 0.000125 moles. Now I know the sig figs, there's too many sig figs, but we're going to leave them for a minute. So this is a limiting reactant problem because you're given the amounts of two reactants. And we can just look at this since we have a 1 to 1 to 1 to 1. If I have 0.0020 moles of nitric acid and I don't have enough sodium hydroxide, that means that the sodium hydroxide is going to be my limiting. This is going to be my limiting reactant. So when I have a limiting reactant problem, I think it's going to be easiest to go ahead and write this out as your ionic equation. So let's write out what happens. Strong acids dissociate, so we have hydrogen ions and nitrate ions. Sodiums dissociate, so we have sodium and hydroxides. Sodiums dissociate, so we have sodiums and nitrates. And then we have some water. Okay. So if I started with 0.020 moles of nitric acid, that means I have 0.0020 moles of hydrogen and 0.0020 moles of nitrate. If I started with 0.00125 moles of sodium hydroxide, that means I started with 0.000125 moles of sodium and 0.000125 moles of hydroxide. I'm not starting with any of the sodium nitrate or water, so we're going to have zeros here. Okay, spectator ions. Spectator ions do not change in a reaction, so the nitrates and the sodiums, nothing is going to happen to them. So at the end of the reaction, after the reaction, I'm going to draw a beaker. That's after the reaction. I'm going to draw it wide so that we can do some calculations in it. We're going to have 0.0020 moles of nitrate, and we're going to have 0.000125 moles of sodium. And we're also going to have something left from the excess reactant. So here's our after. Now, after our reaction, we have 50 milliliters plus 5 milliliters. So we have a total of 55 milliliters here. So what's going to be remaining? Let's look at our net ionic equation. So if we take our net ionic equation, we say H plus OH minus is going to make H2O. And we're starting with 0.002 moles of the H plus and 0.000125 moles of the hydroxide. And because the hydroxide, it's a 1-to-1, and that's less, we're going to use all of the hydroxide. And that means we're also going to use that much of the hydrogen, because that's our change row and that's our stoichiometry. If I use 1 hydroxide, I use 1 hydrogen. If I use 0.000125 hydroxides and run out, I use 0.000125 moles of the hydrogens. So if I do 0.002 and I subtract 0.000125, I get 0.001875, but I have to stop after the 10,000s place there. So I end up with 0.0019 moles of hydrogen left. This is excess hydrogen ions. When the hydroxide runs out, I have 0.0019 moles of hydrogen ions left. So that's the end. And so in my beaker, I'm going to have 0.0019 moles of hydrogen ions. Now, to be complete, I started with no water. I would also make 0.000125 moles of water. And so at the end of the reaction, I would have made 0.000125 moles of water. Okay, but we're going to ignore the water in this question. Okay, so the question number 7 says, what's the concentration? These are the number of moles. That's not concentration. So to get the molarity, remember, the molarity is the number of moles over the volume. So I'm going to take each of these and divide by my volume. And so if we do for the nitrate, 0.002 divided by 0.055, and we get the concentration of nitrate. Let me change the color here. The concentration of nitrate is going to be 0.036. And the concentration of sodium is going to be 0.000125 divided by 0.055, the number of moles divided by the volume, and we get 0.0023 molarity. And then the concentration of the hydrogen is going to be 0.0019 divided by 0.055. And we're going to have the concentration of hydrogen is equal to 0.035. So it has a feeling similar to when we were doing the precipitate reactions, trying to determine, one, we know the spectator ions, the number of moles of spectator ions doesn't change. So we look at our ionic equation, calculate the number of moles of each spectator ion, and put them in the final beaker. And then we do our net ionic equation, and we figure out which ion from the reactants, which one's in excess, and that also goes in the beaker. So that's the answer to number 7. You would end up with 0.036 molarity of nitrate, 0.0023 molarity of sodium, and 0.035 molarity of hydrogen. And by the way, this solution is still acidic because remember, an acid is a solution that has the presence of H+ ions in it. So we didn't neutralize the acid. We neutralized a little bit of the acid, but there's still a lot of H+ ions floating around in that solution. Okay, so that's 3 of the problems from tonight's homework.